everybody, welcome back to our second lesson for the week. So to prepare you for next week, I just want to let you know that we're moving to our regular schedule where you attend 4 periods a day, Monday through Thursday, and Fridays left for any assessments or meetings with counselors or teachers or anything like that. And this is the schedule that as long as we continue home learning that we're going to be moving with for the rest of the semester. This is another reminder about your PhET project and what you should be working on this week. I told you about this on Monday or Tuesday or Wednesday or whenever you listened to my video last. I'm actually going to give you time in class today to work on the balancing chemical equations PhET, but don't forget to also be working on the reactants, products, and leftovers. So for today, we're going to jump right in. These are the materials you need to take out. You need the note taker that says balancing equations. It's number 7 in your at-home packet. This is something that's going to be due via Schoology by the end of the day this week for 15 points in your home learning category. So make sure you're following along with this. Okay, so today our agenda is we're introducing balancing equations. I'm going to give you a little bit of the state of the unit we're in, talk about the importance of balancing equations and how do we do it. So right now, everything that's here in blue is what we have gone through so far in this unit. Talked about predicting formulas, Lewis dot structures, ionic versus covalent bonds, periodic table, and just last lesson we went over naming. Today's lesson is going to conclude this unit on balancing equations, and then we will be completely done with the bonding unit. But this isn't really on your note sheet. What this is coming from is that if we were able to be in class, I would be doing a lab activity with you. So instead, I'm just going to have to give you some background information before we move into balancing equations. So there's 2 key pieces of information that you need to know. There's different types of changes that can go on. One being a chemical change and one being a physical change. Chemical changes is when a substance is chemically changing into another one, and usually we see a chemical formula in an equation actually changing. Where a physical change means that the chemical identity of that product, it's the same, but the physical characteristics might change. It might look different, but boil it down to its atoms and its chemical formula, it's the same. There's also a few kind of types of physical states that you can go through. You have solids, liquids, and gases, which we're all very familiar with. But there's one more called an aqueous substance. The symbol is AQ, and that just means that it's a substance that's dissolved in water. So if we want to look at an example, if we wanted to dissolve sugar in water, we get a liquid, water, plus sugar, a solid. And when you get it, if you've ever done it, it kind of creates this gooey, sugary, watery mixture. That's an example of something that is aqueous. And that is an example of something that is a physical change. So physical changes look like melting ice, chopping wood, creating a mixture, shredding paper. Chemical formula of those don't change, but the actual matter changes its form. Versus chemical changes, if you're burning wood, lighting a match, when a banana rots, putting vinegar and baking soda together to create an explosion or some awesome fireworks, those are chemical changes because a chemical reaction is occurring and new products are formed. But that's a new word there, product, reactant, reactant, product. Those are words that you use typically in just average language, but they have real scientific meaning. So a reactant is a starting ingredient for a chemical reaction, and when we're writing out a chemical equation, the reactant is always on the left. Versus a product, it's a new substance that's formed as a result of that chemical reaction. And in a balanced equation, that's always on the right. So let's say, maybe a lot of you have been doing this lately, that you're going to make cookies. You're going to get some flour, butter, sugar, and eggs, and you're going to be able to mix those all together. Those are reactants. When you're done and you put it in the oven, your end result, if you're a pretty good baker, should be a cookie. The cookie is your product in this case. And what you're using to make the chemical reaction occur is heat. Can the product, which is our cookie, be turned back into the reactants? Have you ever seen a cookie that just turns back into butter, egg, sugar, and flour? No way. So most chemical reactions can only go one direction. We can either go from reactants to products. It's usually unlikely that we go from a product back to a reactant. Another example of this is going to be photosynthesis. When you take biology next year, you're going to learn about photosynthesis in a lot more detail, but it's just looking at what you put into a plant and what comes out of a plant. So plants, you know, they need water, they breathe in CO2, they need sunlight, and in return, they produce sugar and oxygen, which helps us sustain our environment so that we can breathe. We have our reactants here on the left and our products on the right. This is a chemical equation that's showing a chemical reaction. How do we tell if this reaction is physical or chemical? Well, we can look at the properties of the matter that's involved. Did the actual chemical formulas change? If they did, it is a chemical reaction, just like you are seeing right here. CO2 is no longer CO2 in the products. You see C6H12O6, which represents sugar. And so now sugar and oxygen are new chemicals that are being derived from the reactants used to make them. So that actually starts us where you should be on your note taker today, and I have a little bit of a question of the day where I'd like you to work through this table in this chart and the one to the right of it, kind of to warm up, exercise some of the activities that we've been doing over the past couple lessons. So pause here and work on that. Okay, welcome back. So let's go through this. So here we have atoms that we're combining, and we want to look at their oxidation numbers, Lewis dot structures, and formulas. So if we're going to mix potassium and sulfur, we know that for potassium, you have one valence electron with a +1 oxidation number. For sulfur, you have 6 valence electrons with a -2 oxidation number. If I'm going to create a formula based off of that and react the two together, I know that I'm going to need 2 of the potassium to equal out how many sulfurs I have. Here you have selenium and fluorine. Mixing those two together, you get SRF2 subscript. And calcium and nitrogen. Remember, I gave an example in the last video. When you see a 2 and a 3, it can be kind of tricky to think about how many you need, but it's just a multiplication property. If you have a +2 charge on calcium, if you have 3 of those, then you're going to have an overall +6 charge versus nitrogen. If you have a -3 charge and you have 2 of them, you're going to have an overall -6 charge. So we're going to have 3 calciums, 2 nitrogens. You just have to flip-flop the oxidation numbers and add them into subscripts of the opposite atom when you see a 2 and a 3. Next, we're going to review the naming that we went over on our last lesson. So for the first one, we're going to start with a formula. We have P2O4, which is phosphorus, 2 of them, and 4 oxygen. First, we have to figure out, is it ionic or covalent? We know that it's covalent because phosphorus and oxygen are really close together on the periodic table, which means they're more likely to share their electrons. Now, how do we figure out the name of this molecule? Well, it is covalent, so that means we're going to name it using its Greek prefixes. So, for 2, our Greek prefix is di, and for 4, our Greek prefix is tetra. So we get diphosphorus tetraoxide. Remember, we're adding "ide" onto the end to indicate that it is a compound. If we work backwards and we have sodium acetate, I'm going to look, and now I'm going from the name to the formula. So does it contain any Greek prefixes? Nope, doesn't really seem like it. Does it contain a polyatomic ion? I do see a polyatomic ion as acetate in there, and I know that it's ionic because it doesn't create any Greek prefixes, and it has a polyatomic ion. There's acetate. And so I have the chemical formula there. It has a -1 charge, and sodium has a +1 charge. So all you have to do is put the element first, and then you write the formula for the polyatomic ion because they already balance each other out. And then lastly, you have lithium 2 oxide. It is an ionic compound. That means we're going to just write out each of our elements. We're going to name the first one, which is lithium, and the second element, oxygen, but we're going to change the ending to an "ide." All right, lastly, we need to review some of our atomic radius and ionization energies. So if you're looking at these two examples and you're trying to figure out which is smaller, potassium or calcium, well, potassium's here and calcium is right next to it, which means since potassium is further over to the left on the periodic table, that must mean that calcium is smaller, potassium is bigger. For fluorine, we see it here over on the right. Chlorine's directly beneath it, right here and here. So if you move down on the periodic table, things get bigger, which means fluorine must be smaller than chlorine. So now we want to look at which has a lower ionization energy, sodium or magnesium. See them here on the periodic table of elements. You can see their atomic radius. Now for ionization energy, it gets bigger the further up and to the right and upper corner of the periodic table you go. Since sodium is further to the left on the periodic table, it must mean it has a lower ionization energy. For oxygen and sulfur, oxygen is higher on the periodic table than sulfur is, which means sulfur must have the lower ionization energy. Okay, so this is actually a moment for you to interact and work on a PhET simulation here in class today. I'm going to show you how to access it. So I actually need you to pause this video once I kind of show you what you're going through to work on this today. So in order to get to this PhET simulation, all you have to do is type in PhET into your whatever browser, Google you're using, and you're going to want to get yourself to the chemistry page. Once you're there, you don't even have to scroll down. The PhET simulation you need is right here called Balancing Chemical Equations. Go ahead and click play. And you're going to want to start with the introduction. And you must do these 3 things. You must make ammonia, separate water, and combust methane. You're going to want to use these tools. It depends on how you visually like things. This is a balance that shows you whether or not, as you're adding more and more of these molecules, whether or not those molecules are balanced. You could also use this in terms of a bar graph, but I like using the balance. So what this kind of shows you, I'm just going to start by adding 1 of each thing. We want to make ammonia. We have 2 nitrogen and 2 hydrogen. What we want to know is how many of those molecules do we need to make ammonia, NH3. What this tool up top tells you is it kind of shows you how you're unbalanced and even. For nitrogen, you have 2, but you only use 1 on this side. So you have 2 nitrogens here, but here you only use 1. But now here it's saying, okay, but on the product side, you have 3 hydrogen, but we only put in 2 initially. So in order to have a balanced chemical equation, we have to have a balanced number of every single element. So I'm going to kind of start, okay, well that looks a little bit more even. Oh, that's really heavy on this side. Well, maybe I'll add another 1 of these. And I knew what direction I was going with, but you're going to have to play around with the simulation a little bit. Once you have a balanced equation, the PhET will go ahead and tell you and give you a nice, wonderful, beautiful smiley face that you have balanced everything correctly. Then it is your job and opportunity to move forward and play this game, which you can click on the bottom part of the screen. I'm going to let you choose your own level. Depends on how much you would like to challenge yourself. I recommend level 2, but you can choose which level you feel like you're at as you're starting to go through these. And don't forget, this is after you've separated water and combusted methane. So when you're going here, you have different challenges of balancing these equations, and you're going to add some. You might go like here. I'm just going random here for a second. And until you feel like you're good, then you click check. Mine was no good. It's not balanced. You're going to want to try again. You're going to want to work yourself through this game until you've completed all of the challenges that you have. Alright, so now you've had a little bit of an introduction onto looking at molecules, balancing equations. Now here's the logistics. How does this actually work? So we have some different terms. We have the atom, which we know is the smallest part of an element, but a molecule means that we have two or more elements joined together by chemical bonds. So when you're looking at this PhET simulation, here we have one molecule of CH4, and it's this CH4 molecule is named methane. In our products, we have a molecule of carbon dioxide. What we're trying to balance is how many of each individual atom are on each side of the equation. The reactants versus the products need to be equal. So here we see we have 4 total hydrogen on the left side, 2 total oxygen, and 1 carbon. You're trying to create a chemical formula that's balanced with numbers in front of it to indicate how many of those molecules do you need in order to balance the equation. So if we have 2 oxygens on the left, due to the beginning number here that indicates I have 2 O2, here, when I have a molecule as a product of carbon dioxide, I only need one of them because I already have the dioxides. I have 4 hydrogen, but I only have H2O as a product on the right-hand side. So I'm going to need 2 H2O, and when I have 2 of those, I will have 4 total hydrogens on each side. You cannot change subscripts when you are balancing an equation. You can only change the numbers that are in front of the molecules to indicate how many of that molecule you will have. You can't split a molecule in half. It has to be a whole number. So, in review, you can only change the prefix numbers. When you're balancing an equation, you cannot manipulate the molecule. You can only decide how many of each molecule you need, thus only changing the prefix numbers, not the subscript numbers. So let's do an example of balancing the following equation. Here's some examples and rules. First, you're just going to want to always look for any singletons, an atom that only shows up in one location. So for this first example, I'm going to take care of balancing sulfur first, then carbon, then oxygen, because I only see sulfur in one location on the left side, my reactants, and only in one location on the right side in my products. Right now for sulfur, I have 1 in my reactants and I have 2 sulfurs in my products. So I'm going to write that I have 2 sulfurs, and that's going to even out my sulfurs. And this is kind of like playing a little bit of a puzzle game, because when I have 2 sulfurs, that then means that I have 4 total oxygens in the reactants. So I need to look to the products and I need to say, well, I need to have 4 oxygens in the product. Well, now in the products, I have 4 oxygens and I have another, so that's settled, but then that also means I have 4 carbons plus the carbon that's attached to the S2. Which means on my products, or my reactant side, I'm going to want to have 5 carbons. Then I need to check myself. Okay, how many on the left side do I have? I have 4 oxygens, I have 2 sulfurs, and I have 5 carbons. On the right side, it's the same. That means I get a go-ahead and I have a balanced equation. Let's try another one. Here we have C3H8 plus O2 on our reactant side, and on our products we have CO2 and H2O. I'm going to start looking at my CO2. I see that I have 3 carbons on my reactants, So I'm going to want to make sure I have 3 carbons in my products. That's the easiest one to work with first. When I add 3 to my CO2, that gives me 6 oxygens plus the 1 oxygen on the H2O, which is 7 oxygens. It's really difficult to create an odd number of something. I also know that I have 8 hydrogens in my reactants, so I'm going to go ahead and make how many hydrogens I need. I have 4 times 2 of the hydrogens for the subscript. So I have 8 total hydrogens in the products, 8 total hydrogens in the reactants, which leaves me with 4 times 1 oxygen. So I have 4 oxygens for H2O, and 3 times 2 oxygens, I have 6 oxygens there, which means I'm going to check if I'm balanced. I have 10 oxygens in the products. If I change my O2 on the reactant side, the left side, I will also have 10 oxygens, which helps me completely balance out my equation. So for today's activity, you're going to fill out the backside of balancing equations to completely understand this lecture and go through it, and you're going to turn this in. You're going to take a picture of it and turn it into a Schoology assignment or email it directly to me. Now, of course, I'm going to be available on Google Hangouts if you need any help working through any of these equations. When you are done with today's activity, you should work on your test review guide, which is also due at the end of this week. So by the end of the day on April 24th, you should have turned these 3 things in via Schoology or email to me. The naming activity we completed in last lesson, the balancing equation activity, and your bonding test study guide, all worth 15 points each, 45 points total in the home learning category on Infinite Campus. Please email me, log into Google Hangouts with any questions you guys have. If not, have an awesome rest of your week.